Hi guys, welcome to part 1 of quick revision notes for thermodynamics. In thermodynamics, the syllabus is divided as in first law we have closed system and open system. In second law we are going to study heat pump, heat engine and refrigeration and entropy, and then we are going to study properties of gases and liquids. So let's get started. So according to zeroth, before starting that I would like to tell that in heat transfer we have studied the rate of heat transfer, while thermodynamics deals with energy transfer, in form of heat and work, heat or work. So this is the basic difference between heat transfer and thermodynamics. So the four laws of thermodynamics are zeroth law, first law, second law and third law. So this zeroth law deals with the temperature. Second law is based on internal energy. First law is based on internal energy, second law based on entropy, and third is based on absolute entropy values. So according to zeroth law, it states that two systems are in thermal equilibrium with each other when they are in thermal equilibrium with third system. What it basically means is that if system A is in equilibrium with system C, and system B is in equilibrium with system C, so system A would be in equilibrium with system B. Temperature is same for the three system. So the basis of this law is temperature measurement, which is temperature equality, and no transfer of heat take place. So zeroth law is used to calculate thermometer based questions. So next is our first law, which is law of energy conservation. So because this video is for quick notes, so I'm not going to dive into details. I am going to make video later on for detailed video based on the topics, but right now we are just quickly going through the numericals. To solve numericals, we are quickly going through the formulas only. So for first law, we have this formula, which is del Q minus del W is equal to du, where our del Q is net heat transfer during cycle, del W is net work transfer, and du is internal energy or energy of the system. Then first law for a closed system is given as it is energy balance between the system and the surrounding. So plus minus Q is being heat transfer plus minus work is equal to change in energy of surrounding. So our net internal energy would be Q plus W, which would be equal to energy of the system. Next we have is delta U is equal to Q minus W. So U being internal energy. So if we would divide and multiply this equation from mass of the system, then we would get m into small u2 minus u1, capital U being the internal energy. When it is divided by m, it gives specific internal energy. When heat is divided by mass, it gives specific heat. Small q is heat transfer per unit mass of system, Q by m, and small w is our work done per unit mass, which gives us small w. So this gives us this equation, u2 minus small u2 minus u1 is equal to q minus w. So specific flow of work is calculated as pressure into specific volume, and specific enthalpy is sum of internal energy, specific internal energy small u and specific flow of work H is equal to U plus PV, pressure into specific volume. Next is for first law for our open system. This is our system in which M1, H1, V1, Z1 are entering and M2, H2, V2, Z2 are leaving, where M is mass flow rate, H is specific enthalpies, H1 and H2, and V is velocity, and Z is height of in and out flowing mass, and Q is the heat provided to the system and W is the work done by the system. So capital Q by M would give us small q, which is rate of heat transfer, and capital W by M would give us small w, rate of work, and E is our total energy. So energy balance would be dE change in total energy with respect to time would be energy flowing in minus out plus work done minus Q, heat. So energy flowing in would be M2 H2 plus half M1 V2 square M2 V2 square plus mg Z2. This is basically our kinetic energy plus potential energy, half mv square kinetic energy, and mg Z being the height, mgh is potential energy, plus mass into specific enthalpy. This is the flow of energy in minus flow of energy out, which is mass into specific enthalpy m1 h1 plus half m1 v1 square kinetic energy plus m1 g z1 potential energy plus work done minus q. So now we have just simplified the equation. So what we basically get is rate of change of total energy, that is dE by dt, would be delta summation of kinetic energy, potential energy plus mass into specific enthalpies plus W minus work done minus Q. This is for our open system. Then we have open steady state. So steady state means that time rate change of all quantities is 0 and mass is conserved. Mass and total energy do not change with time. That means dE by dt would be 0 and m1, m2 mass would remain same, is equal to m. So the equation that we have calculated for open system, we are going to put our m1 and m2 is equal to m and dE by dt would be 0. So basically our equation comes out to be h2 plus v2 by 2 square plus gz2, z being the height, minus h1 plus v1 square by 2 plus g z1 is equal to, we have divided our q and w with m. It was q by m, which is small q, and w by m, small w, being small q being specific heat transfer rate and small w is specific work transfer rate. Now capital C, which is heat capacity, given unit is joule by Kelvin. This is an extensive property. So it is amount of heat necessary to raise temperature by 1 degree Celsius. Capital C, heat capacity, is Q by delta T, amount of heat required to raise temperature by 1 degree Celsius. And heat is directly proportional to amount or mass of substance. So according to first law, du, change in internal energy, is equal to dq minus dw, and in case of work is, we know that, is equal to pdv, pressure into change in volume. So for constant volume, at constant volume, when heat is added at constant volume, then CV, this is capital CV, heat capacity at constant volume, would be del U by del T at constant volume, which is equal to del Q by del T at constant volume. Then at constant pressure, H is equal to U plus PV, H being the enthalpy, is equal to internal energy plus pressure into volume, and dH is equal to dQ minus VdP. So at constant pressure, specific heat capacity would be del H by del T at constant pressure is equal to del Q by del T at constant pressure. Then we have specific heat, small c. Capital C is heat capacity and small c is specific heat, and it is an intensive property. It means that heat required to added to substance to raise its temperature. Heat capacity, which is capital C, is equal to specific heat into mass. So similarly to work and heat transfer, when heat capacity capital C is divided by mass, it gives us small c, which is specific heat capacity. So we know that our heat transfer Q would be mc delta T. Q being heat transfer, m mass, C specific heat into change into temperature. The limitation of first law is that first law do not give information whether transportation of energy actually take place or not. So next we have our second law. Before starting second law, we have few terms which I'm going to discuss. R we know is universal gas constant, and RC is specific gas constant, which is R by M, and thermal efficiency is work by Q. These are few conversion units. 1 bar is equal to 10 to the power 5 Pascal is equal to 100 kilopascal, and kilopascal is equal to 10 to the power 3 Pascal. Kilojoule per second is kilowatt, which is equal to 1000 watt, and kilojoule is equal to 10 to the power 3 joules. These are few conversion units which are going to become handy in question solving. So thermal efficiency is work by Q. Then work done by electrical energy is I square RT, which is current square into resistance, and Q of electrical heat is I square RT. Then if in any question slow work is given, which means it would be a quasi state, so in that case work would be equal to P into dV. Then all these things are going to be used in question solving. So when heat is transferred into the system, it is taken as positive, and when heat goes out of the system, it is taken as negative. So when heat is transferred from system to surrounding, it is taken as negative heat. When work done is on the system, then it is taken as negative. When work is done by the system, then it is taken as positive. Compression work is taken as negative and expansion work is taken as positive. Please take a screenshot of these. These are going to come handy in question solving. Next we have second law of heat transfer. Guys, these are just formulas to solve question. I am going to make detailed notes video later on, so please subscribe to my channel to get notification whenever I would upload detailed notes for that. So now let's proceed to second law of thermodynamics. First we have heat pump. So starting from heat pump, a heat transformer is providing some heat Q. It is at temperature T, and two reservoirs are there at high temperature TH and low temperature TL. So net Q would be Q1 plus Q2, and this heat pump is based on Clausian inequality. So it states that Q by T is equal to 0 if it is a reversible, and and less than 0 when it is irreversible. So where our this is del Q by T. So our del Q is basically heat transfer at a part of system boundary during a portion of cycle, and T is our absolute temperature at the boundary part. So the inequality states that there is no internal irreversibility as system executes cycle, and inequality applies when there is an internal irreversibilities are present. So basically Clausius inequality is mathematical form of second law of thermodynamics for closed system undergoing a cyclic process. So we are going to balance our Q and T. So Q by T, which is if we notice this part, Q by T is heat supplied, Q by T minus Q1 by TH. This is going out, and Q2 by TA for low temperature reservoir. So the equation would be Q by T minus Q1 by TH minus Q2 by TL is equal to 0. For better understanding of these formula, I would suggest you guys to watch practice question which I'm going to upload, so that you can easily understand that where these formulas are going to be used. Next we have heat engine. Before that, I would state one more point, which is when there are more than two reservoirs, heat transfer is done, whether it is a cyclic device, whatever cyclic device it is pump, refrigerator or engine, so reversible or reversible. When there are more than two reservoirs, heat transfer is done. So next we have heat engine, which is based on Carnot theorem. So in case of heat engine, this is our engine, and we have to transfer heat from TL to TH, from low temperature reservoir to high temperature reservoir, and for that some work or power is supplied. So to calculate COP being coefficient of parameter or Carnot coefficient, COP is equal to Q by W, which is desired effect by work input. So for COP of heat pump, we have TH by TH minus TL. So in case of heat pump, our this diagram is for refrigeration, because we are transferring heat from low temperature to high temperature. Cooling process is taking place. So yeah, COP for heat pump would be TH by TH minus TL. Work input is TH minus TL, and the desired effect is high temperature, which is TH. And in case of refrigerator, desired effect is TL by work input is TH minus TL. Next we have Carnot engine, which is most efficient cycle. So in case of Carnot engine, heat goes from high temperature to low temperature. So to calculate the efficiency for Carnot engine, it is equal to 1 minus T low temperature minus upon T high temperature, which is equal to 1 minus heat of low reservoir upon heat of high reservoir, which is equal to 1 minus 1 by R to the power gamma minus 1. R is our compression ratio. Next we have entropy. Entropy is basically measure of amount of disorder in a system, and it is so Clausius inequality for a reversible cycle, which we have studied for heat pump as well, is inequality sign. This is inequality sign into rho Q by T for reversible. 0 is equal to 0. So S is our entropy, and delta S would be S2 minus S1. So dq of reversible reaction by T is equal to 0. So ds would be equal to dq reversible by T, and delta S that is change in entropy, would be equal to T Q reversible by T from state 1 to state 2. Entropy change between two states, two equilibrium states 1 and 2. This is the formula. So to calculate the efficiency, which we have already studied for our Carnot engine, it is efficiency is 1 minus temperature out by temperature in is equal to 1 minus heat out by heat in. So from this equation we can say that Q in by T in for reversible is equal to minus of Q out by T out for reversible. So equating this, we get Q in by T in plus Q out by T out for reversible reaction is equal to 0 and not equal for in case of irreversible. So next we have relation between internal energy and entropy, relation between U and S. So delta S we know is S2 minus S1, which is equal to dq by dt for cyclic reversible cycle from 1 to 2, and we know that dq is du plus dw, okay, and du is d ds minus p dv. For work we can write work is equal to p dv minus of p dv. dw we can write as minus of p dv or vdp, and dq by t is equal to ds. So from there we for dq we can put dq is equal to tds. So from here we get our change in entropy is equal to integration of du by dt, internal energy with respect to time. So entropy balance for equation for a closed system would be delta S would be S2 minus S1 for a cyclic reversible cyclic equation from 1 to state 1 to 2 for dq by dt plus sigma, where sigma would be 0 if it is reversible reaction and less than 0 in case of irreversible reaction. So dq by t for a reversible cycle 1 to 2 state 1 to 2 is basically entropy transfer. Direction is same as heat transfer, and sigma is entropy production. It states about entropy production, entropy generation due to internal irreversibility in the system. Then entropy for ideal gas, H is our enthalpy is equal to U plus PV. We know that du is equal to dq for reversible minus p dv. So taking the differentiation of this equation, we get dh is equal to du plus pdv plus vdp. Okay, now we can write du as dq reversible minus pdv. So solving this equation, we get our final equation is dh minus vdp is equal to dq for reversible reaction. For case of ideal gas, dh is cp into dt by t minus r dp by r. ds is cp into dt by t minus r dp by p, and ds by r, that is change in entropy by universal gas constant, would be equal to cp. This is for ideal gas, ig is ideal gas, cp by r dt by t minus dp d ln of p. So the final equation, this is the final equation, delta S by r, change in our entropy by universal gas constant, would be equal to integration of cp specific heat for ideal gas by r into dt by r integrated from temperature T0 to T minus ln of P by P0 final pressure by initial pressure, where m delta S is mCp ln T2 by T1. Entropy balance for open system is given as rate of entropy in minus entropy out plus entropy generation is equal to entropy accumulation. So entropy in would be summation of m in into Si entropy in minus summation of m out mass out into summation mass out into entropy out plus S naught being entropy generation is equal to ds by dt entropy accumulation. So this was our Clausius inequality for entropy, and the criteria of irreversibility is first law condition of thermodynamic of a process can be stated as condition of given irreversible process that lead to violation of law of thermodynamics, then that process is irreversible. So Clausius inequality, we know that dq by dt for a cyclic process is less than or equal to 0. We have studied before. Then efficiency for reversible reaction is 1 minus T out by T in, which is equal to 1 minus Q out by Q in. For irreversible reaction, the efficiency is net work by Q in, which is equal to 1 minus Q out by Q in. So efficiency of reversible process is more than efficiency of irreversible process. Why? Because by Carnot theorem operating between two same temperature reservoir, it comes out to be efficiency of reversible process is more than efficiency of irreversible process. So if we put in the values of our reversible equation, 1 minus T out by T in is greater than 1 minus Q out by Q in, we get our equation Q in upon T in plus Q out upon T out less than 0, which we have also studied a few minutes back for our Clausius inequality. Then we have Gibbs free energy, which is H minus Ts for a system. Henliot's free energy given as A is equal to U minus Ts. In irreversible process, which is not isothermal, our Henliot's energy would be delta U minus delta Ts minus T delta S, which is equal to dQ. dA would be minus PV minus SDT. It is not going to be used in that many questions, but Gibbs energy is important, which is G is equal to H minus Ts.